Okay, this is the recording for the DFJ callback model. I'll click on this. Okay, so this is an implementation of the DFJ model, but just in a different way, a way that's actually a little bit faster. I'll run cells from before. Actually, what I can do, I can copy paste probably some of this code from the other DFJ model. So the initial two matching relaxation, copy that over. But I won't optimize. I'll do that in a little bit. So I'll just update here. Oh, I need to run the cell. Okay. So I've created a model and I've added just the degree constraints. So I haven't added any of the subtour elimination constraints from the DFJ model quite yet. Okay. So instead of repeatedly solving an integer program and getting the solution, finding some subtours, adding cuts, going back to the integer program, solving the integer program again from scratch. That was kind of the approach that we did last time. So you would end up having to solve 3 or 4 or 5 or 6 different integer programs. But using callbacks permits us to just solve one integer program. And really the idea here is that we're going to essentially use one branch and bound tree. But in each of the nodes of the branch and bound tree, we will have to tell Gurobi if we like the solution that it's finding at that node of the tree or not. So essentially, we may find these solutions where you have subtours at the nodes of the branch and bound tree. And if so, we have to essentially write a function or code that will tell Gurobi to add that constraint for that subtour kind of in the process of branch and bound. Okay. So we need to create what's called a callback function, which is what Gurobi is going to, this is basically the function that Gurobi is going to call at each one of these branch and bound nodes. So I'm going to call it subtour elimination. That's what it does. And it has, anytime you're doing a Gurobi callback, you need 2 arguments. One of them is the model object, and the other one is something called where. And so where will tell you essentially what kind of branch and bound node it is. Or kind of, it'll tell you where the solver is in its solve process. So first, we will check if the LP relaxation at this given branch and bound node has your solution. And this is an LP-based branch and bound algorithm that Gurobi is implementing. And so at any one of these nodes, it could solve the LP relaxation. And if the LP relaxation is fractional, then we're not going to bother doing anything there. We're going to keep letting Gurobi branch. But if it is integer, then we're going to check it and see if it has subtours. So if where is grb.callback.all. So this means if it's an integer solution, in that case, we will retrieve the LP relaxation solution at the branch and bound node. I'll call that xval. So I need to do m.cb for callback, get solution. And I want it for the model's x variables. So this we'll set in just a second, but essentially just think of this as like the x variables. Okay, so once we found an integer solution, then we retrieve what that integer solution is, and then we ask which edges are selected in that solution. So that is tour edges, that's what we'll call it. This is all the edges E. And it's all edges for which xval of E is should be 1, but again, floating point, so we'll just check against 0.5. And normally we would just write g dot edges, but essentially because this function only permits us to pass the argument for the model object m, we're really going to end up storing g as part of the model object. So we'll do that in a second, but for right now, you can think of this as just g dot edges. So after we get the tour edges, we essentially check if it's connected or not. If it's not connected, or maybe I could just go ahead and loop over all of the components for each subtour, add a elimination constraint. So for every component in connects.connected components, this is of edge-induced subgraph by the tour edges. And again, think of this as just g.edge subgraph, but I had this m._, because we're just passing the model object itself. So we look at all of these components in our solution, and if that component is small, if it's not a full tour, then we add the constraint over those inner edges like before. All these edges ij that are in our graph, for which I is in the component and j is in the component. And here's where we would normally do add constraint. It would sum all of those x variables across the inner edges. And that should be at most the length of the component, or the number of nodes in the component, minus 1. Okay, so this is what I would normally write, but because we're in a callback, we have to do this a little different. So one is that, again, not x, but m._x. The other difference is that we don't just add constraint, we do callback lazy. Okay. So really the reason why we have to use this is because this constraint is not added initially to the model. It's only added at certain parts of the branch and bound tree. And so just because of how Gurobi works internally, it needs to know that this is a constraint that's added during a callback at some node of the branch and bound tree and not kind of initially or at the root of the tree. Okay. That is good for our function. And in order to use this, we need to do a couple things. So one, we need to set the lazy constraints parameter in Gurobi to 1. So we're just telling Gurobi that yes, we're using lazy constraints, which is stuff like this, where we're adding the constraints later on. I also need to specify that the callback that we're using is that subtour elimination function. Then, again, since this function is only being passed the model object, I need to add the graph G and these X variables to the object, graph object, or sorry, the model object itself. So I need to have something, I need to store X as part of the model object, and I need to store the graph G as part of that model object. Then when I go to solve, instead of doing m.optimize, I need to pass an argument telling Groby that, hey, I'm using this callback. Okay, so now I should be able to solve this. And you'll see that, I mean, it's all very quickly, and it added 12 constraints. So in total, throughout the entire branch and bound tree, it had to add 12 subtour elimination constraints. Okay, so now I can get my solution. For en g dot edges if value is at least 0.5, and then I'll draw it. And this should be optimal, and we don't have to do that kind of iterative process where we add constraints and resolve, add constraints, resolve. All of that's handled in one branch and bound tree just by calling this function. So these callbacks are a really powerful kind of advanced technique